Welcome you all in this fifth lecture on metric spaces. In the first four lectures, we have seen that how we can define the idea of distance in a non-empty set, a non-empty arbitrary set, and how we can have several kind of distance functions on a non-empty set. We have seen several examples of matrices, or you can say the metric spaces. Now today we will see that how we can define the distance between two sets. For example, if you have suppose this is your any set, okay, here you have this is any set, let us call this set is your A, this set is your B. So what would be the distance between these two sets? So again we have to define the idea of the distance. The idea of the distance means which parameter we are using. So we are using the parameter which we called it is a metric, that is the function d. So if you have a function a and b, then the distance between a and b we will denote it by rho ab. That is the distance between the set a and b. And it is defined as, of course, keep in mind these two sets are the subsets of a metric space xd, okay, where x sub a and b are the subset of x and x is equipped with a metric d, okay. So with this one we can define the distance between a and b is equal to the infimum over, you take the infimum over x is in a and y is in b dxy. That is to say, you take any point x, okay, here you take point y and you find this distance, okay. So this distance is your not the ordinary distance, but it is the distance measured by the metric d. Okay, so similarly you take all these distances from here to here, take any point here, any point is here, and then finally you will see that from here to here this is the shortest distance, okay, that is the infimum of all these distances, and that is called the distance between the set A and the set B. So this way we define the idea of the distance between two subsets of a metric space, okay. So here is this is the rho AB is the distance between the set A and B, which is equal to the infimum of dxy, and infimum is taken over x is in A and y is in B. Of course, because the infimum, this d is a metric, so it is symmetric, that is to say dxy is equal to dyx. So here is we can take rho AB. So a rho AB is equal to rho AB is equal to rho BA. So this is same from here by using the definition of a metric. We can say that the distance from a set A to the set B is same as the distance from the set B to the set A. Now if instead of taking a set, suppose here you have a point x, okay, here you have a set, you can take a set B, okay. So what would be the distance from a point x to the set B? So that is your, again you can treat this set x, the point x, as a set consisting singleton element, and now you use the same definition as this one, okay. So here is then you can say that rho x b is equal to, you take the infimum of d x y and you take y is in b. So this way you can define the distance from the point x to the set B, and which is must be equal to this distance. So this way you can define the distance from a point to a set B, okay, and it is we are denoting by instead of writing the singleton set, we can write this as rho x b, and it is the distance from the point x to the set B. Okay. So, now you can see that for example, if we are considering suppose a real line, okay, let us consider a real line. Here is I am considering the real line, okay, this is of my 0, okay. So, let us take a set, okay, this set, okay. So, this is your set 1 set and another set is this one. So, here is this is x is strictly greater than 0, here is x is strictly less than 0. So, this set is A suppose and this set is B. Then what would be the distance between A and B? If you take the infimum, then you can find the rho AB must be equal to 0. But A and B, they do not have any common point. Okay. So, it means that we can conclude, we can reach to the conclusion that if the rho AB, if the distance between two sets A and B is equal to 0, then it does not imply that A and B have a common point. And similarly, if you take the A, suppose if you take the point, this is your x, here is suppose this x is equal to 0, okay. So, x is equal to 0 and B is the set of all points x which are strictly greater than 0, okay. Then you can see that the distance between rho xb, the distance from a point x to the set B is equal to 0, but x does not lie in B. So, it means that we can conclude that if rho xb, that is the distance from a point x to the set B is equal to 0, then it does not imply that x belongs to B. Okay. So, this is the way to so this is the way we can conclude these things. So, let us see here is how we can then we have the idea of the diameter of a set. What does it mean, the diameter of a set? Suppose you have a set, this is your set, okay, this is your set, okay, let me call this set is your A. So, what would be the diameter? So, diameter of the set you take any 2 point, okay, you take this distance, take this distance, from this point take this distance, from this point to this point, this point to this point, this point to this point, and take all the distances and take the supremum of such distances. Okay. So, supremum of such distance is called the diameter of A, and the diameter of A is denoted by delta of A, which is equal to the supremum of dxy, xy is in A. So, this way we can define the diameter of a set A. And if the diameter of a set A is finite, that is to say, if there exists a constant k such that delta A is less than k, which is finite number, then we say that the set, this set is bounded. In other words, A is bounded if its diameter is finite. Okay. In other case, otherwise it is called unbounded set. Okay. In particular, the metric space X with metric D is bounded if the set X is bounded. Now, we have several examples of a bounded set. So, we can have several examples. For example, you can see that the real line with the usual metric space, okay, the real line with the usual metric space, is your unbounded metric space. Okay, but the intervals, closed interval AB, open interval AB, closed open interval AB, closed open, closed interval AB, all these intervals are bounded. But the closed interval 0 infinity or open interval minus infinity closed interval A, these two intervals are not bounded, but rest of the intervals are bounded. And as we have seen, in the space S is the S is the set of all real or complex number sequence of all real or complex numbers, and we have defined the metric on S by dxy is equal to summation I runs from 1 to k 1 over 2 raised to the power n, okay, mod of xn minus yn divided by 1 plus mod of xn minus yn. Okay, and then this with this one, then the space of all sequences of real or complex number is a bounded space, because the distance between any two element in this space dxy must be strictly less than with this series. Okay, and now you can very easily see that the discrete metric space, because in the discrete metric space the distance is either 0 or 1. So it is always less than or equal to 1. So if you take any 2 point, you take the supremum that would be less than or equal to 1, because it is either 1 or 0. So it is less than or equal to 1. So it is a bounded, and the diameter of this set is 1. Because the diameter means you take the supremum of any 2 point, it would be either 0 or 1. So the supremum is equal to 1, and therefore the diameter of a discrete metric space or discrete metric space is 1. Okay, and so it is a finite, it is a bounded metric space. Now let us consider a set S. Okay, so here we consider the set S. Okay, rectangle. Okay, xy. So it means that we are considering this rectangle. Okay, here is from 0 to 1 and 0 to 1. So this is your rectangle. So let us call this set is your S. And then with respect to the usual metric, what is the diameter of this set? The diameter of this set must be equal to this distance. And because this is 1, so this must be equal to under root 2. So this is the diameter of the set, this with respect to the usual metric. Okay, if we consider the taxicab metric, the taxicab matrix means you remember that it is equal to dxy is equal to the mod of x1 minus y1 plus mod of x2 minus y2. So x1 minus y1 is this distance which is equal to 1, and x2 minus y2 is this distance which is equal to 1. So with respect to the taxicab metric, the diameter of this set is 1 plus 1, it is equal to 2. So this is the diameter is equal to 2. Okay, with respect to the max metric means that dxy is equal to maximum of mod of x1 minus y1 comma mod of x2 minus y2. So here is x1 minus y1 is 1 and x2 minus y2 is 1 and the maximum is 1. So with respect to the max metric, the diameter of this set is 1. So you can see that the diameter with respect to different kind of matrices is different. It is not same. With respect to the usual metric, the diameter of this set is under root 2. With respect to taxicab metric, the diameter is 2. With respect to the max metric, the diameter is 1. And of course, if we consider this set, okay, as a subset of a discrete metric space, Okay, because we can always consider this R square as a discrete metric, then you will see that because in the discrete metric space the maximum is 1, so the diameter with respect to discrete metric, the diameter of this set is 1. Now, if suppose we have a metric space XD, okay, suppose XD is a metric space, then with the help of this metric, which is already given on the set X, we can always define several other matrices. How we can define? We can do in this way, that we can define d1 xy is equal to dxy divided by 1 plus dxy. Okay, so we can define this metric, and I have already mentioned in the exercise in the previous talk, I have mentioned that if we define d1 xy is equal to this one, then d1 is a metric on x. And similarly, we have also given in the exercise that d2 xy is equal to minimum of 1 dxy is also a metric. Okay, so this way d1, d2 are matrices on x. So with the help of the given matrix, we can define another metric, we can define other matrices, that is d1 and d2. And these two matrices, okay, with respect to the metric d1 and with respect to the metric d2, x is bounded. So in other words, x d1 or x d2, okay, they are bounded metric spaces. That is, x is bounded with respect to metric d1 as well as with respect to d2, irrespective whether d, okay, original metric d is bounded or not. Okay, so this is a very important thing, but the important thing you will see whether this metric is bounded or not. This is always bounded, because this, okay, because whatever is dxy, we are dividing by 1 plus dxy. So this is always less than or equal to 1. Okay, similarly, this, whatever is the metric, because we are taking the minimum of this one, so this is d2 is always less than or equal to 1. So d2 is bounded and d1 is also bounded. So d1 and d2 are bounded irrespective of the metric d is bounded or not. And then I have here is mentioned several exercises, and these are very simple exercises, and I will leave these exercises for you, and you can see that here is just I have mentioned that determine the distance from the point 3,4 to the set 0 close interval 0, 1 cross close interval 0, 1 with respect to different kind of the matrices, that is to say usual matrix, taxi matrix, max matrix and discrete matrix, and you can calculate in the same way as we have done in this example. Similarly, if you consider the set A is equal to this thing, and then find the diameter of this set, and that you can also calculate by in the same way as we have done here. And then you see here is we have A and B are two non-empty subset of a metric space X. D, prove that the following statement, that is to say the diameter of A is equal to 0 if and only if A is a singleton set. Very simple, because the diameter of A is what? Diameter of A is equal to the supremum of the distance between any 2 points of the set A, but the set A is singleton, so it is equal to supremum dxx, because x, if suppose x is containing A singleton set, so A must be like this. Okay, so if you take the diameter, so diameter of A is equal to the supremum of dxy and xy in A. But because this is singleton set, so this must be equal to x. So xx is equal to, it is equal to 0. So whatever is it is always equal to 0. So the diameter of A is always equal to 0. Okay. So we can prove that the diameter of a set A is 0 if and only if it is a singleton set. Second property is that if x is in A, y is in B, okay, then the distance between the set A and B is always less than or equal to the distance between x and y. This is by the definition of the distance between the set A and y. How you can do? You can, though that the row of AB is equal to the distance from this to this is equal to the infimum of x is in A and y is in B dxy. Okay, so we are taking the infimum over this. So by the definition of the infimum, because this is the infimum value of dxy, so from here you will get this thing very easily. So no problem at all. Okay, so I am removing this one. Then if A is a subset of B, then you can prove that the diameter of A is a subset of the diameter of B. Very simple. And the diameter of A union B is less than or equal to the diameter of A plus the diameter of B plus the distance between A and B. And if the A intersection B non-empty, that is to say if and B are subsets of a metric space X which are not disjoint, then the diameter of A union B is less than or equal to diameter of A plus diameter of B. And we can see that this triangle inequality can be proved very easily, no problem. So several all these are very simple. I just take the D and E part. So let us take A and B be arbitrary elements of A and B respectively. That is to say, let us take any point X, in let us take X in A and B in B, okay, and let's take X, Y in A union B, okay, because we are considering the sets in the following way, that the set A and B, so you have a set A and you have a set B, because the A intersection B is non-empty. So here we take X is in A and now we are considering X and Y are 2 points in the intersection of this one. If X and Y are both in A, okay, so we are taking, we are taking X and Y, we are taking X and Y in A union B, okay, we are X A union B. So X can be in A or X can be in both, or Y can be in A or B or in both. So if X and Y are in A, okay, then clearly the diameter dxy is less than or equal to the diameter of A. Similarly, if X and Y both are in B, then dxy is less than or equal to diameter of B. As from here you can see, from here we can see this one, okay. Now if X is in A and Y is in B, okay, both are in different set, then we use the triangle inequality. How we can use? We can use the dxy is less than or equal to dxa plus dxy, okay, and then this is always less than or equal to, we can add the dxab, because this is a non-negative term, so we can add, so this term is less than or equal to this one, but this is less than or equal to the diameter of A, this is less than or equal to the diameter of B, so this is less than or equal to this one. Similarly, we can take if X is in B and Y is in A, we can have the dxy is less than or equal to diameter of A plus dab plus diameter of B, okay. So from here we can see that from this one and this one, we can see that the dxy is less than or equal to diameter of A plus DAB plus diameter of B for all xy in A union B. And therefore, you see this is true for all xy. So, we can take the supremum both the side. So, if we take the supremum, then the diameter of A union B is less than or equal to this term plus this one for all x is in A and y is in B. So, it means what? It means that this is because we are taking this, and again you take the supremum over all x is in A, y is in B. So, this is the distance from distance between the set A and B. So, this distance is the diameter of A union B is less than or equal to diameter of A plus rho AB plus diameter of B, which is nothing but it is equal to your part D. And now for the part A, we can see that if A intersection B is non-empty, then we have the distance between A and B is equal to 0, okay, because the infimum distance it is equal to 0, and so this rho AB is equal to 0, it means that this term is equal to 0. So, what we get, the diameter of A union B is less than or equal to the diameter of A plus diameter of B, provided that the A intersection B is non-empty. So, this way you can prove these exercises. So, try to do all these exercises by yourself first, and if you could not succeed to get the answer, then try to see these solution sets. Okay. So, that is the main things which we have done for the diameter of a set. Okay. Now, before I am going to the next section, I stop over here and I will continue this next section in the next lecture, that is lecture number 6. Okay, thank you very much.